here to pay tribute to Blaine participating in this conference, and I'm particularly happy to talk about this subject here because Blaine has two particular connections to it, one of which is apparent from the title, that this subject is something that grew out of his work with Misha Gromov, but also there's a personal connection in that the whole reason why I got interested in this has to do with a conversation or series of conversations I had with Blaine and Misha more than 20 years ago in Paris, I believe. And it was really talking to him that got me interested in this, and this has turned out to be a very interesting direction for a lot of my work. So I'm very grateful to Blaine for having pointed out this problem to me. So if you haven't heard of it, the Gromov-Lawson conjecture has to do with the classification of manifolds according to the possible values of the scalar curvature. So we're going to be talking about Riemannian manifolds. And while there are very interesting problems for non-compact, complete manifolds, I'm not going to talk about them here. And I'm just going to concentrate on the case of closed manifolds. So first of all, let me just remind you a few things about scalar curvature. This is sort of classical stuff you learned in the first course in differential geometry, but let me just point out a few things. So the scalar curvature is the weakest of all curvature invariants. It's the, roughly speaking, the average curvature at a point, the trace of the Ricci tensor. And in dimension 2, it's equivalent to knowledge of the Gaussian curvature, but in higher dimensions, it's a much weaker invariant than the Ricci curvature, or certainly than the full curvature tensor. But one interesting property you can use even to you could use this in fact as a definition, is that the scalar curvature is the first interesting coefficient in the expansion of the volume of a small geodesic ball. So when the scalar curvature is positive, it means that this is the volume of a ball in Euclidean space, this is the volume of a ball in your Riemannian manifold. So positive scalar curvature, which is what I'm going to be talking about, means that small geodesic balls have smaller volume than they would in Euclidean space. However, unlike the case of Ricci curvature, in the case of Ricci curvature, you actually get bounds on the volumes of balls out to some reasonably large size. In the case of scalar curvature, all you know is that this is the first coefficient in an expansion, and you basically have no effective way of telling how small means here. So, well, this is an interesting fact that doesn't really tell you very much. But another fact about scalar curvature, which is trivial but useful, is to point out that in a Riemannian product, scalar curvature adds. Because the Ricci tensor of a Riemannian product is just the block direct sum of the two Ricci tensors, and then when you take the trace, the two components add. And this is going to have the consequence that the property of positive scalar curvature is absorbing in products. In other words, suppose M has a metric of positive scalar curvature, and you don't know anything whatsoever about N, then you can always rescale M so that it has very small diameter, and that makes the curvature very big. And then this term will swamp whatever you have on the other side. So if M has a metric of positive scalar curvature, then so does M cross N regardless of what N is. And a lot of the facts that we know about positive scalar curvature have to do with this plus extensions of it. In other words, it's not necessary to have an exact product. You can have an approximate product, or you can have a manifold that's approximately covered by approximate products. In other words, a fiber bundle or something like that. So a lot of the results about positive scalar curvature basically just boil down to this simple observation. Now, now we start getting to the interesting part. So, yeah, right. Which two facts? Right. That's right. Oh, but here. Well, remember, this is talking about balls, and when you look at something in terms of products, you're basically looking at cylinders. Yeah, I mean, a product of two balls is not round, so yeah, it has corners, so yeah, it's not quite the same thing. Yeah, yeah. Yes. You can do the calculation, it's not different. Anyway, what I want to talk about is this. So there's a trichotomy. All manifolds, all compact smooth manifolds can be divided into three classes. Okay. So let me tell you what the three classes are. These three classes are illustrated by the classification of surfaces that you, real dimension 2, not complex dimension 2, that you learn in first course in geometry and topology. You know the classification of surfaces is according to the genus. There are two kinds of surfaces with positive, we're talking about compact surfaces here, so there are two kinds with positive Euler characteristic, the sphere and the projective plane. There are two with zero Euler characteristic, the torus and the Klein bottle, and then all the remaining ones are have hyperbolic structures. So in those cases, in the hyperbolic cases, the scalar curvature is negative. Here you can make it 0, and here you can make it a constant and positive. And now you might say, well, what about arbitrary metrics? Those are just the nice metrics, but suppose you take an arbitrary metric, but then you immediately observe that because of the Gauss-Bonnet theorem, the integral of the curvature is up to a normalizing factor, the Euler characteristic. So if the scalar curvature has constant sign, then the sign has to match the sign of the Euler characteristic, so therefore you have these three different classes. So the first class are manifolds that admit a metric of positive scalar curvature. And in dimension 2, by this Gauss-Bonnet argument, we know exactly what those are. Now, what is remarkable is a theorem of Chasm and Warner, which says the following two things. First of all, if you just have a Riemannian metric which has non-negative scalar curvature, as soon as it's strictly positive at one point, then you can arrange to have it strictly positive everywhere. So there's no distinction between those two cases. The second thing is that once in dimension 3 and up, once you have a metric of positive scalar curvature, then you automatically have metrics, for example, of negative scalar curvature. That's automatic. Any manifold dimension 3 and up has metrics of negative scalar curvature, so there's no obstruction to that. That's a little bit of a surprise when you just think about the two-dimensional case, but a little calculation shows you that that is indeed the case. So if in dimension 3 and up, once you have one metric of positive scalar curvature, then it turns out that any C infinity function whatsoever is a scalar curvature of some metric. So there are no constraints on the scalar curvature at all in this class. So we're going to be mostly interested in determining what is this class of manifolds, a class of manifolds that have metrics of positive scalar curvature. This is class A. Class B are things that are not in class A, but still have a metric of non-negative scalar curvature. But by what I said before, that means the scalar curvature is identically zero everywhere. And in fact, the same theorems of Chasm and Warner show that in this case the metric has to be Ricci flat. So things like tori, and it'll turn out Calabi-Yau manifolds and things like that fall into this class. And then there's a third class of manifolds which are not in either of these cases, where there's no metric of non-negative scalar curvature at all. Okay, so the problem is which manifolds belong to these various classes. And you might think that there are several problems here, but really there's only one. The big problem is to determine what's in class A. Once you know what's in class A, then class B is almost classified, because these things, because of the Ricci flat property, they're all the manifolds that do not fall in class A but have a Ricci flat metric, and those things for the most part have exceptional holonomy, and we know quite a bit about them. So class B is largely understood, and then class C is just everything else. But for the time being, in higher dimensions, it's not clear that there's anything that's not in class A at the moment, right? I mean, we haven't shown you any reason why something shouldn't be in class A in dimension 3 and up. Dimension 2, you have the Gauss-Bonnet argument. So this problem was attacked independently by Gromov-Lawson and by Shane and Yau. And in particular, Blaine and Misha wrote 3 papers about this problem of classifying manifolds of positive scalar curvature. And the whole subsequent history of the subject really depends on these 3 papers. So 2 of them are in the Annals in 1980, and the other is in the ITS Journal in 1983. And so what I'm going to talk about grows out of these papers. Now, just talking about what's in those papers actually would take up a full lecture in itself, so I'm not going to do that. But let me just give you a sort of quick outline of some of the things that are in there. So one thing is something called the Surgery Theorem. I'll talk about that. That was independently proved by Shane and Yau. Then there are extensions of the Lichnarowitz-Hitchin theorem. I'll talk about what that is. Then there are some special results on 3 and 4 manifolds that have to do with special phenomena that occur in low dimensions. I'm not going to talk about that either. And then there are a lot of results on complete positive scalar curvature metrics on non-compact manifolds. That's very interesting, but I'm just going to skip that in the interest of time. So in other words, I'm going to concentrate on these 2 things and what grew out of that. And just for purposes of making the slides more compact, I'm going to abbreviate positive scalar curvature, since that phrase is going to come up over and over again just by PSC. Okay? So that's what it stands for. I'm not trying to create some new acronym. This is just because I ran out of room on some of the slides. So it just stands for positive scalar curvature. So here are the sort of basic facts you need to get started. So first there's the surgery theorem. Since it's possible that not everybody here knows what surgery is, let me just explain that first. So in high dimensions, there's actually a good classification theory of manifolds, which grows out of the work of Milner and Curvaire and Browder and Novikov, which goes under the name of surgery theory. And the basic idea is this. If you have some manifold, you can create new manifolds out of an old one by the following procedure. Suppose you have an embedded sphere inside a manifold. And suppose this sphere has a trivial normal bundle. So if this is a manifold Mn, and over here you have a sphere Sk, then the normal bundle of an embedded sphere, if the normal bundle is topologically trivial, is just a copy of Sk across a disk in the complementary dimension. Right? Now, given this product of a sphere and a disk, the boundary of this thing is a sphere cross another sphere. And now you notice there's a kind of funny symmetry here. This thing can also be thought of as the boundary of dk plus 1 cross Sn minus k minus 1 by switching the disk to the other side. So now you can do the following modification procedure. You take this little region here, you cut it out, and replace it by a dk plus 1 cross Sn minus k minus 1 that has the same boundary. And that creates a new manifold out of an old one. And the whole classification of theory of manifolds is based on the study of this modification procedure, which is called surgery. Just as an indication of why this is important, you see the classification theory of manifolds comes from Morse theory, analysis of Morse functions. And when you start studying a Morse function, if you look at the various level sets of the Morse function, most of the time those keep the same topology. The topology of the level sets in the Morse function only changes when you hit a critical point. And when you hit a critical point, what happens to the topology is exactly this process of surgery. So that explains why every manifold can be built out of this surgery procedure, and so that's why this is so important. Yes?
What's the co-dimension of that surgery?
So, all right, so now here we have a K sphere inside an N manifold. So K is called the dimension of the surgery, and N minus K is called the codimension. So now I can explain what the surgery theorem says. It says if you can make one manifold out of another one by surgeries, and the codimensions of the surgeries are all greater than or equal to 3, so that means n minus k is at least 3, then the property of having a metric of positive scalar curvature is preserved under this process. Yes, when you go from one critical level of the Morse function to the next one, the way the topology changes is by means of a single surgery. Let me illustrate that with the simplest possible example. Namely, suppose you have a little piece of a 2-manifold and you look at level sets of a Morse function. So most of the time, you have things like this. Now you might hit a critical point like this. And, here are the level sets up to the critical point, and then you get to the critical point here, and now all of a sudden the topology switches. And if you analyze the process of going from here to here, you'll see it's exactly a surgery. All right, so why this codimension greater than or equal to 3 condition? Let me just give you a quick intuitive reason. You see, if you're going to cut this thing out and glue something back in so as to preserve the property of positive scalar curvature, you need in particular a metric of positive scalar curvature on the thing that you're gluing, and then you need to match it up on the boundary. So what is it that you're gluing in? You're gluing in this. N minus k greater than or equal to 3 means n minus k minus 1 greater than or equal to 2, which means that this sphere over here is positively curved. If n minus k minus 1 were equal to 1, this would be a circle and it would be flat. That wouldn't be any good. Then this thing here would not have a natural metric of positive curvature on it. But if n minus k minus 1 is greater than or equal to 2, then this thing is positively curved for its natural metric. So you have a natural metric of positive scalar curvature on that thing you're gluing in, and you can arrange to perturb things around the boundary to get this thing to match. Now, to get this to actually work is quite technically complicated, but that's sort of a rough idea. All right, so that's the first basic ingredient. And the other basic ingredient is the calculation by Lishnerowitz of the square of the Dirac operator. So if you have a spin manifold with a Dirac, then of course it comes with a Dirac operator. Lishnerowitz observed that if you square the Dirac operator, the leading term, of course, is something that looks like a Laplacian. It's covariant differentiation followed by its adjoint. And then that's the leading term, and then this is a second order operator now, so now you should have some correction terms of orders 1 and 0. But it turns out all the order 1 stuff cancels out, and all the order 0 stuff cancels out except for the scalar curvature divided by 4. So what's that? Truly astounding fact, which you just discover just by expanding everything out. I mean, it's a horrendous calculation in Clifford algebra, but that's just the way it works out. So in particular, you see that if the scalar curvature is strictly positive, that means that, since this operator, of course, is obviously non-negative, that means that the square of the Dirac operator is bounded away from 0. So it means that the spectrum of the Dirac operator is bounded away from 0. In fact, you have a bound on the spectrum given by the scalar curvature, and therefore all the index invariants of the Dirac operator have to vanish. So, for example, in dimensions divisible by 4, the so-called ordinary index of the Dirac operator is what's called the A hat genus, and that has to vanish for a manifold with positive scalar curvature. So now you finally see an obstruction. Not everything has a metric of positive scalar curvature for this reason, because of the fact that it implies that there are no harmonic spinners. So now, without giving a sort of precise statement of the Gromov-Lawson conjecture, because the original versions of the conjecture were somewhat imprecise anyway, I'll just say that one of the things you see from these papers of Gromov and Lawson is that you get the fundamental idea that if you have a closed manifold, first of all, if it's simply connected, basically what they proved was that if it does not have a spin structure, so there's no Dirac obstruction, then it always has a metric of positive scalar curvature. But if it does have a spin structure, you have these Dirac obstructions, and it wasn't stated explicitly in their paper, but it was sort of implicit that the conjecture is that those are the only obstructions. And in general, what we expect is that if you have a closed manifold, let's say it's oriented, and it has a classifying map to the classifying space of the fundamental group. So this is sort of a basic part of the structure, which I guess if you're not a homotopy theorist, maybe you're not used to thinking about, so maybe I should say something about it. But you see, it's going to turn out that we have to keep track of fundamental group data. And the way you do that is that if you have any, doesn't have to be a manifold, any space at all with a certain fundamental group, then you can always construct a map from M to a classifying space for the fundamental group, which is an isomorphism on pi 1. So what's a classifying space for the fundamental group? This is a k pi 1 space. In other words, it's a CW complex that has pi as its fundamental group, and all the other homotopy groups are 0. So just as an example, if the fundamental group is free abelian, the classifying space of a free abelian group is a circle. So in other words, I'm just saying that if your fundamental group is Z, then you can find a map from M to S1, which is an isomorphism on pi 1. It's very easy to do it in that case. And the general case is done basically by putting that together with some obstruction theory. So now the guess that Gromov and Lawson had was that the answer to whether or not a manifold has a metric of positive scalar curvature should depend on the homology class that M defines in here under this classifying map. And the question of what homology theory you have to take depends on whether you're in the spin case or not. So in the oriented case where the universal cover is non-spin, it's just ordinary homology, and in the spin case, it's K-theory homology. So it's a homology theory that's dual to real K-theory. And the reason is that K-theory is basically where these index obstructions for the Dirac operator live. So let me say a little bit about what you can now do. So here is sort of the basic fact. This theorem here has a lot of stuff hidden under the rug in it. And it includes basically everything that was in the first Gromov-Lawson paper plus Stoltz's solution of the simply connected case plus a thesis of Reiner Young, which has never been finished. So this theorem, unfortunately, doesn't have a complete proof in the literature, although Stoltz and I are sort of writing out a proof since it's sort of clear that Young is never going to publish it himself. But anyway, when you put all this stuff together, what it says is the following. It basically confirms this original guess of Gromov and Lawson that the question of whether or not M has a metric of positive scalar curvature only depends on a suitable homology class that it defines in the homology of the fundamental group. And the question of what homology theory you need to use depends on a combination of W1 and W2 data. First two Stiefel-Whitney classes. So let me start with the easiest case first. Suppose M is non-orientable and its universal cover is not spin. Universal cover not spin means there are no Dirac operators. Non-orientable means M is oriented for mod 2 homology but not for ordinary homology. So the only available homology theory here is mod 2 homology. And sure enough, it turns out that M admits a metric of positive scalar curvature if and only if the homology class defined by M in the homology of the fundamental group with Z mod 2 coefficients lies in the subgroup generated by manifolds with positive scalar curvature. So what that's saying is a rather amazing fact. If you have two different manifolds that represent the same homology class, and one of them has a metric of positive scalar curvature, then the other one has to also. So how do you prove this? Well,
that subgroup looks like explicitly at all?
What?
Do you know at all what that subgroup looks like explicitly?
Well, I'll talk about that later, but yeah. So let me just mention some of the various steps that go into the proof of this theorem, because this is actually a very remarkable theorem. So the first part is that you have to go from this part was basically done by Gromov and Lawson. You have to go from the Surgery Theorem to the Boardism Theorem. So the Boardism Theorem says that if you have two manifolds M and M prime, let's say here's your B pi over here, and suppose M is boarded to M prime over B pi. That means there's a manifold with boundary that interpolates between them such that you can extend the map like that. And then what conditions you put on this manifold depend on the W1 and W2 data. So for example, in this case over here, you would just use unoriented boardism. In this case, you would use oriented boardism. Here you use spin boardism. So if you have a boardism like this, and M prime has a metric of positive scalar curvature, then so does M. And the way you prove this is by using the Surgery Theorem. several times. You see, basically by that fact I mentioned to you before about Morse theory, if two manifolds are boarding to each other, that means you can get from one to the other by a sequence of surgeries. In this particular case, we've set things up so that because of these W1 and W2 conditions, you can arrange for these surgeries to satisfy the codimension condition also. That's the tricky part. So then you can go from M prime to M by surgeries in codimension greater than or equal to 3, and then by the surgery theorem, you can carry the metric of positive scalar curvature over across the boardism. So that's the first step in the theorem. Now, the second step is you have to go from boardism to homology. Boardism is a sort of a primeval homology theory. It represents homology in the original sense of Poincare, but it's very hard to work with. So in boardism, by definition, homology classes are represented by manifolds, but that's not the same thing as singular homology, where homology classes are represented by singular manifolds. So you have to go from boardism to homology, and it turns out that to actually prove that, then, see, once you've gone from here to here, you're now reduced to something in algebraic topology, and now you can use all the machinery of algebraic topology, even though that wasn't present in the original geometric problem. So once we've arrived in the realm of algebraic topology, we now can localize at a prime p, and it turns out you have to split into two cases depending on whether p is equal to 2 or p is odd. So then you have p equal 2 and p odd, and there are different techniques that come in here in these two different cases. In the case where p equal 2, p is equal to 2, you have to use the technique of Stolz, which basically proves that so now you have, let's look at the spin case. You have the spin boardism, and that maps to KO homology. This is connective K theory. So KO, at the prime 2, KO is a little summand in this. This is a huge thing. This is fairly small. In going from here to here, there's a huge kernel. But the remarkable theorem of Stolz is that that kernel is represented by manifolds that have a fiber bundle structure where the fibers are copies of HP2. HP2 is a manifold of positive scalar curvature, so by the Fibration Theorem, which is sort of a modification of the product result that I mentioned in the very first slide, you can then show that all of that kernel is represented by stuff of positive scalar curvature. So therefore, if you're interested in what might not have a metric of positive scalar curvature, it's only the image over here that matters. So that's basically the proof at the prime 2. At odd primes, the proof is due to Young, and it uses a different idea, and that goes back to an idea of Dennis Sullivan and others, which says that homology somehow or other has gotten out of boardism by introducing singularities. So homology classes in boardism are represented by manifolds, and in ordinary homology they're represented by singular manifolds. So you get from one to the other by allowing singularities in your manifolds. So what you prove here is that homology is the same thing as boardism with singularities. So in other words, it's represented by things like that, but where you allow various kinds of singularities in the boundary. Then you show that all of the singularities you have to add can be represented by things of positive scalar curvature. And then again, by using the Boardism theorem again, you can carry that metric of positive scalar curvature. You said metric of positive scalar curvature here. You also have metric of positive scalar curvature on the singularities. So you sort of regard that whole thing as the boundary of the non-singular part of this boardism, and then you can carry the metric across. So that's sort of the idea of how this works. So there's quite a bit of work that's hidden in here, but anyway, this sort of gets us down to the original idea of Gromov and Lawson, that the question of whether or not a manifold has positive scalar curvature only depends on its homology class in the fundamental group. And what homology theory you have to take depends on the W1 and W2 data. So once again, here are three cases. There's the little KO case, the HN case, and the HN, the Z-mod 2 coefficients case. I haven't given you a complete list, that there are other cases also. I mean, it might be that the manifold is non-spin, but its universal cover is spin. So then you have sort of twisted KO, and that's even more complicated, but the same idea basically works. Sorry, what? You don't see them in the geometry. You only see them in the algebraic topology. You see, Boardism is represented by this really complicated spectrum, which is usually called MSO or M-spin. So this lives in the world of stable homotopy theory. Stable homotopy theory, is attacked by methods of category theory and so on. So in this stable homotopy category, you can localize. So that the localization is done over there. It's not done in the geometry. Okay, so this is the sort of big tool that now enables us to get toward a classification. And this, so lots of cases of this, by the way, now answer our question completely. For example, if the manifold is simply connected, then this case doesn't arise. You only have two cases here. The original theorem of Gromov-Lawson about the non-spin simply connected case immediately follows from this, because if B pi is just a point in the simply connected case, then there's nothing in the homology of a point. So nothing gives you an interesting homology class. So everything, therefore, is a metric of positive scalar curvature. So this is their original theorem sort of recast in really complicated language. In the spin case, it's only the image. Now, if B pi is a point, you get KO lower n, and these groups KO lower n are given by the following table. So they're equal to Z for n congruent to 0 mod 4, Z mod 2 for n congruent to 1 or 2 mod 8, and 0 otherwise. This is for n positive. But in the simply connected case, the class that you get over here in KO lower n in this group turns out to be just the index of the Dirac operator. So in that case, we get back this theorem of Stolz that says that for a simply connected spin manifold in dimension 5 and up, you have a metric of positive scalar curvature if and only if the index of the Dirac operator is equal to 0, which we know is a necessary condition. So now it's a sufficient condition as well. So that completely solves the problem. Okay, but what about the non-simply connected case? That can be very complicated because the homology of the fundamental group can be very complicated. So now we have to say something about sort of more complicated Dirac obstructions. Yeah.
Is there a list of things you don't want to admit scalar curvature representing
Well, the necessity just comes from the Leshnerowitz theorem. In other words, remember we said that if you have a spin manifold, then you have a Dirac operator, and you have index invariants of the Dirac operator that live in here. And if these things are non-zero, then you can't have a metric of positive scalar curvature. So that's the basic obstruction. There are a few other cases where we know there's an obstruction that can't be gotten that way, and those other cases are handled using either the Shane-Yao minimal hypersurface method or Seiberg-Witten theory in dimension 4. But I'm mostly talking about dimensions 5 and up because surgery doesn't work very well in dimensions, at least in the smooth category in dimension 4. Well, in the simply connected case, this map is onto. In the general case, for general fundamental group, this map Yeah, if you look at the map from example, omega spin star of b pi to ko star of b pi, in general, for general fundamental group, this map is neither onto nor injective. So there's a huge kernel, but also doesn't hit everything. Of course, the things that aren't hit, you don't have to worry about, because it means they didn't come from manifolds. So if they didn't come from manifolds, there's nothing to talk about. But among those things that are hit, then you have various other obstructions, which I'll talk about now. So that brings us to basically the conversation I had with Blaine back about 20 years ago. So that's sort of on the next slide. So suppose you're in the spin case. So that means you have a Dirac operator. So you have a homology class defined by n in connective K-theory, and you can periodize it to get a homology class in periodic K-theory. Now, on the other hand, you have the group ring of the fundamental group, and well, if the fundamental group is infinite, then you have to complete the group ring, and you get this thing called the group C-star algebra. If you don't know what that is, just ignore it for the time being, because we're mostly going to talk about the case where the fundamental group is finite, and then you don't have any completion to do. But anyway, this thing is a Banach algebra over the reals, so it has K-theory in the sense of Karoubi. And there's something called an assembly map, which is defined in a completely functorial way. This was defined by various people. I won't try to give you a complete list. From the KO homology of the fundamental group to the KO of the group ring. So this thing's called the assembly map. On the other hand, you also have this periodicity map. You can periodize connective K-theory, which is a non-periodic theory, to this thing by inverting the Bott element. So that's the periodicity map. So now, where do the other obstructions come from? Most of the other known obstructions come from this fact over here. If you have a metric of positive scalar curvature, and you take its homology class in little ko, then you periodize it, move it forward under assembly, so you get something over here. This thing, the image, turns out to be the index of some kind of generalized Dirac operator, with coefficients in some mysterious flat bundle. Since it's the index of a Dirac operator with coefficients in a flat bundle, the Schnerowitz calculation applies, and if the scalar curvature is strictly positive, then that index invariant has to vanish. So if you have a metric of positive scalar curvature, then when you're finished, moving all the way over to here, you have to get 0. So that's where the other obstructions come from. In the simply connected case, of course, b pi is a point. This map over here is an isomorphism. This map over here is an isomorphism as long as n is positive, and then nothing much is happening. So we just get the old Dirac obstructions. But one thing that comes out of that, well, this wouldn't be any good if we didn't know something about this thing called the assembly map. But let me just say that it's conjectured. This is basically what's called the strong Novikov conjecture. If pi is a torsion-free group, then it's conjectured that this assembly map is always injective. In fact, always split injective. In fact, for torsion-free groups, we even expect it to be an isomorphism. So, therefore, this assembly map, which seems rather mysterious, actually is fairly harmless if you believe that conjecture. So in the torsion-free case, assembly map shouldn't be necessary. And that is known in many, many cases. So we get the following theorem out. So suppose the assembly map is injective. That's, as I said, that's called the strong Novikov conjecture. It's almost equivalent to what goes under the name of Novikov conjecture in surgery theory. And suppose the periodicity map is injective. That's also often true. Then M admits a metric of positive scalar curvature if and only if the Dirac obstruction vanishes. So in this case, we have a complete solution of the original Gromov-Lawson conjecture. And this, so this was what was originally conjectured, and we know that this is true for many, many fundamental groups. So for example, for free abelian groups, surface groups, lots of hyperbolic groups, fundamental groups of nil manifolds, there are lots of cases for which this works. So in those cases, the problem is completely solved. But there's the opposite extreme of finite groups. And for finite groups, the assembly map is very far from being an isomorphism. So what happens there? So for finite groups, you don't have to complete the group ring. So this is just the ordinary group ring. And also you can reduce. So look at KO reduced to KO of the reduced group ring. Now it's divide out by the sort of trivial copy of R that comes from the trivial representation. And then this reduced assembly map, for example, is always 0 if pi is of odd order. So then the assembly map doesn't give you anything. There are no Dirac obstructions other than the ones you have in the simply connected case. And also, for finite groups, the periodicity map is almost never injected. So this problem also breaks down. So things get very complicated, it would seem. So let me just say what you can say about this. So a while ago, I made this sort of audacious conjecture that the Dirac obstructions should be everything. Well, I mean, I knew at the time that this is not true for general fundamental groups, but for finite fundamental groups, there's some hope that this might be the case. Even for finite fundamental groups, I have to say I don't believe it myself anymore. But although we do know that it's true in some cases, which I'll talk about. But you can do better if you build periodicity in. You see, one of the problems is the geometric problem doesn't have any kind of periodicity in it. But as soon as you go to periodic K-theory, capital KO instead of little ko, then there's Bott periodicity built in, which seems to be totally artificial in the problem. I mean, the original problem, why should things be periodic mod 8? There doesn't seem any reason for that. So my collaborator Stoltz had the nice idea that why not try building in periodicity in the geometric problem and then seeing what you can do. So then we have a so-called stabilized problem. So we fix something which we'll call Bott manifold, which is a representative of the Bott class in KO8. So this is a simply connected spin manifold with A hat genus equal to 1. And the reason for using the letter J for it is that, again, connection with other things mentioned in this conference, the natural choice for this J is a Joyce manifold of exceptional holonomy, spin 7. So this is something that's Ricci flat, but it can't have a metric of positive scalar curvature. So it's in this sort of intermediate class B. Has a Ricci flat metric, but it can't have a metric of positive scalar curvature because the A hat genus, which is the index of the Dirac operator, is non-zero. They're harmonic spinners. So we'll say that M stably admits a metric of positive scalar curvature if you can get a metric of positive scalar curvature after multiplying by copies of J. So multiplying by copies of J is sort of like inverting the Bott element. And then you periodize the problem. And the stable conjecture is that this should be necessary and sufficient. And as far as the stable conjecture is concerned, actually we know quite a bit. So yeah. So you see, multiplying by J8, as far as the KO class is concerned, is like multiplying by the Bott class. So allowing yourself to multiply by this is the same thing as formally inverting the Bott element. So here are a few known results. Let me just try you a few interesting things. So these are just about manifolds with finite fundamental group now. So Botvinnik, Gilkey, and Stolz show that the original conjecture, that the Dirac obstructions are everything, is in fact correct if you have a fundamental group with periodic homology. So periodic homology means that the CELO subgroups of the fundamental group are as simple as possible. They're either cyclic or generalized quaternion groups in the case of equal to. And then Stolz proved that this is sort of building on work that I did with Stolz in the case where the fundamental group is torsion-free. The stable conjecture holds for arbitrary spin manifolds as long as some other conjecture called the bound-Kohn conjecture is true. And the bound-Kohn conjecture sort of lives in a different domain. It lives in the sort of world of C-star algebras and so on. So, I mean, we've sort of gotten so far away from the original geometry that, you know, at this point, you could say that the problem is solved in the sense that it's reduced down to something in a sort of completely different area. So the bound-Kohn conjecture, by the way, is true. So let me just tell you what groups satisfy the bound-Kohn conjecture. For example, any discrete group that can be embedded in a Lie group satisfies the bound-Kohn conjecture. So that's already a huge class. Fundamental groups of, well, if your fundamental group is has a subgroup of finite index, which is hyperbolic in the sense of Gromov, then again it satisfies the bound-Kohn conjecture. So there are huge classes of fundamental groups for which this is known. On the other hand, as Mr. Gromov pointed out to me many times, you know, if you're making conjectures about completely arbitrary groups, there's no reason to expect anything whatsoever to be true. So probably this is false for groups, so to speak, chosen at random. In other words, if you just choose a presentation of a group totally at random according to some probabilistic procedure, probably, you know, this would go wrong a lot of the time. Well, but who knows, you know. So the stable conjecture ought to be true, but it's the unstable conjecture that we want to get our hands on. And as far as the unstable conjecture is concerned, you can use a result of Krosigk and Schultz that again makes it possible to localize to particular primes. Again, this is something that doesn't seem to be present in the geometric problem, but once you've reduced to algebraic topology, you can then localize at various primes. And so it turns out, because of various transfer arguments and stuff, that it's just enough to prove that you want to prove the general conjecture, it's just enough to prove the case of a P group. All right, so, but what about P groups? Well, those are already pretty hard. So I'll try to sort of quickly say a little bit about what Botvinnik and I have been doing in the case of P groups. Yes? Well, the point is, in order to check the Gromov-Lawson conjecture for a particular group, it's just enough to check it for all the CELO subgroups. That's what I meant. So you can reduce the case of a P group. So the simplest kinds of P groups are what are called elementary abelian P groups. These are just, if you like, finite dimensional vector spaces over a field of P elements. And for simplicity, I'm just going to stick to the case of P odd and M non-spin, although the theorem we're going to prove actually holds in the spin case also. It's a little more complicated. So in this case, you have to, by that theorem I mentioned before, in order to prove the conjecture, you want to show that all homology classes that are hit by Boardism classes are represented by manifolds of positive scalar curvature. Now, one of the complications, of course, is that not every homology class is hit by something in Boardism. The map from Boardism, the homology is not onto in this case. So, for that reason, you can't really work directly in homology. You have to work in homology and Boardism simultaneously, which is part of the reason why this thing gets so complicated. But there are Kenna theorems for both homology and Boardism that enable you to sort of work your way up one rank at a time. So you can sort of work up. You know the case of r minus 1, and you can get to r by using the Kenna theorem here and here. And in the Kenna theorem, there are two kinds of terms. There are the tensor terms, which are easy. Those just correspond to products of manifolds. No problem with that. But the real problem is what do you do with the Tor terms in the Kenna theorem, which are what make this thing so complicated. So Tor terms, it turns out, are represented geometrically by things called Toda brackets, or sometimes they're called massey products also. And the way you construct them is the following. So suppose you have two different Boardism classes. Let's say they're both of order p. Then you can form this thing called the Toda bracket. And the way you do it is as follows. P times m, by assumption, is a boundary. So P times m bounds something. And P times m prime also bounds something. So then you take the product of m prime with something bounding Pm, and you take the product of Pm prime, of something bounding Pm prime with m, and then you glue those two things together along their common boundary, and that thing's called the Toda bracket. So what? Because of the assumption that its Boardism class was of order p. Right, that's the basic assumption. So you have to find a way to represent, to get positive scalar curvature on Toda brackets. So that's sort of the basic geometric ingredient that's needed to do anything here. And let me just quickly say how you do that. So the sort of basic technical tool is this. You have a Toda bracket like this. Well, by that rescaling trick I mentioned before, you can get a metric of positive scalar curvature over here, and similarly you can get one over there. The only problem is you rescaled in two opposite ways, so the metrics now don't match on the boundary. So what you do is you have to interpolate between them by replacing this thing in the middle by a little cylinder, and on the cylinder you use a trick which already was in the Gromov-Lawson papers. You sort of stretch the cylinder out and you distort it like that, and then if you do this the right way, then you can show that you can get the right kind of metric. So we're just about out of time, so let me just conclude with the theorem here. So in the homology of a elementary abelian group, you have certain bad homology classes, which are called the toral classes. These are things represented by tori. For these homology classes, we actually know absolutely nothing. So we don't really know whether a homology class which is toral is represented by a manifold of positive scalar curvature or not. And it may be that it's not, in which case we need to look for some new kind of obstruction. But basically what we can show now is that except for the toral classes, everything else does satisfy the conjecture. And since the toral classes stop in dimension equal to the rank of the fundamental group, that means if you fix the fundamental group, then for all sufficiently large dimensional manifolds, the original conjecture is true. So this is what I've written here is the non-spin case, and you can prove the spin case by very similar technology. But what's so strange about this whole subject is that you have such a mixture of techniques from such totally different fields. So in just a few of the ingredients, we have the original geometry, which came into constructing metrics on Toda brackets. Then you had a lot of algebraic topology and sort of stable homotopy theory. It's used to analyze these Boardism groups and so on. And then there's also the index theory, which provides the opposite side of the picture groups. Hope that gave you some idea of what's going on in this subject. would be nice. Unfortunately, it really doesn't work except in cases we already knew about. You see, if you fix a fundamental group, there are an awful lot of manifolds with that fundamental group. I mean, the basic fact that you learn differential topology is that any finitely presented group is the fundamental group of some 4 manifold. So, or some manifolds of dimensions 4 and up. So, there are a huge number of manifolds with a given fundamental group, and we only understand a very, very small fraction of them. So the problem is to get at the ones you don't understand out of the ones that you do understand. And that's a very tricky thing. That's where we need all Boardism theory.